rep because people thought it was very unstable, and that's why I put down that it was the infamous 8-point algorithm. Now, you might say, well, why can I do with just 8 equations? I've got 9 unknowns. Well, remember, p f p prime equals 0. I can scale the f any way I want, which means, for example, I could set that last value to a 1. Not a very good way of doing things, but it does mean that if you gave me just 8 points, I'd have 8 equations, and because I set the last one to 1, I would have 8 unknowns, and I'd be able to solve it. If I have more than 8 equations, right? So then I've got this, let's suppose I've got n. So I've got n equations with 9 values that are homogeneous. Have we seen that before? Yes. Remember when we solved very early on, when we were trying to solve for the total calibration matrix between the world and the image, and we had the M matrix, and we said, well, there's 12 elements in here, but there's not really 12, right? There was really only 11, but if we used a whole bunch of points, we talked about you could set one element to M to 1, but that wasn't such a good way. What was a good way? The SVD, remember you've got this A times M equals 0, or in this case, A times F equals 0. You take A transpose A, take the singular value decomposition, or you just find the eigenvectors, and you pulled out the eigenvector with the smallest eigenvalue. We've actually seen this now 3 times. I did it explicitly for you in the very first example, so you can go take a look at that. But that's how you solve it. And by the way, you would typically use more points than just 8 or 9, or you use however many points you have. So you solve this, and what happens? Well, your point matches aren't exact, are they? No. So you solve this, get an f. With an f, I can draw some epipolar lines, right? And if I used, and these numbers were meant to represent coming from that picture, I would see this, okay? And that's technically called a mess, all right? Because you'll notice that the epipolar lines, they're not all intersecting at that single point, are they? No. Why not? Well, I'll tell you. So here I have the same system I had before, 2 camera centers, some point out there, and these are my 2 image planes, okay? Now, go in your Wayback Machine, well, not so far back, just a few lectures back. How do you map from one plane to another plane? Well, I told you before that if you have 4 points on one plane and 4 points on another plane, and you knew their mapping, you would then have the total mapping between the 2 planes, and that was called what? That was called a homography. Right? It took 4 points to get a homography from one side, from one plane to the next. All right? So we're going to pretend for a moment that we know the homography, we'll just call it H, that goes from the plane P to the plane that has P prime in it. Okay? So we're going to pretend that we know that. All right? And the other thing we're going to do is we're going to say for some point P here, L prime is going to be the epipolar line in the prime frame that goes through this epipole E prime. Okay? So that's the 2 things I've set up. I'm going to pretend that I know my homography, and I'm going to also say that that's the epipolar line. All right? Now we do a little math. Okay, so L is that epipolar line. So how do I find this line? Well, remember, this is a line that goes between 2 points. If you remember, in projective geometry, if I have 2 points and I want to find the line that goes through them, what do? I just take the cross product. That was one of the cool things about the projective geometry. You gave me 2 points, take the cross product, you get the line. Give me 2 lines, take the cross product, you get the point that's the intersection between them. So here I just wrote that L prime is just going to be the cross product of E prime and P prime. But wait, we said that there's a homography H, okay, that maps between P prime and P. So I'm just going to substitute H times P for P prime. Okay, no problem. Then I'm going to use something else you learned, actually, just last time, all right? We said that a cross product can be written as this little matrix operator, right? Right. Okay, great. So that says, just erase that L prime is just equal to this cross product operator on E prime times H, the homography, times P. Right? Right. But now, I said L prime is the epipolar line in the prime frame for the point P. That's what this is, right? This is the epipolar line for this point P, all right? Well, we just learned that L prime is just Fp, right? F is the fundamental matrix times P. We learned this like 5 slides ago. That was the one that we repeated like 17 times. Well, okay, L prime is equal to this nonsense over here on the left, and it's equal to Fp on the right. That means that this nonsense on the left, E prime cross product matrix times H, is equal to the F matrix. Well, remembering a little bit from your linear algebra, that means that the rank of this thing is going to be the rank of this thing, and this is rank 2. Told you this would come up before. Remember I said to you, and this was an exercise we left for the reader, that this little cross product matrix operator, where we took the A and we distributed amongst the 3 by 3, multiplied it by B for A cross B, and I said one of the things that we're going to need later, see I wasn't lying, is that the rank of that cross product operator is 2. So that means that the rank of F, which is just this matrix times H, is also 2. F is not full rank. But before, when I was solving for the elements of F, I didn't enforce that in any way. It's a 3 by 3. And whether if you use the SVD or whatever you do, it's not going to make it become a 2-rank matrix even though it's a 3 by 3. So we have to fix our F to be a rank 2 matrix. So how do we do that? Fortunately, that's really pretty easy. It's pretty simple to fix that linear solution that we did before. So do what we said before, solve for F, and you can do SVD, where at that minimum eigenvector, or you can use the linear thing where you set it to a 1, although I don't like that method, okay? You solve for an F. Then what you do is you decompose your F using SVD again. This is another SVD, another singular value decomposition, and you're going to get out 3 terms, all right? Remember, SVD gives you U, D, V transpose. V is the lower dimensional orthogonal matrix of all unit vectors that are orthogonal to each other. U is also orthogonal, but of the full dimension. Now, what did D stand for? No, not Dalmatian, not dysfunctional, despite what you might think. D stood for diagonal. Okay, so it breaks down, it gives you a diagonal matrix. Now, if F is really a full rank 3 by 3 matrix, D is going to come out as a diagonal matrix with 3 non-zero elements. And D, normal SVD, is produced in a decreasing magnitude. Okay, so it goes from largest to smallest. So what we do is we take the D that comes out, and I just wrote that as RST here, okay? And T is smaller than S, which is smaller than R. And what we're going to do is we're going to create a new D, D hat, and just set that least value to 0, because it was supposed to be 0, because that would be a rank 2 F, would have a R, S, and 0, so we make it 0. Great. Once we've done that, we can build a new F, which I'll call F hat, using the same U that we got the first time, the same V that we got the first time, but we substitute in this new D, right? D hat, which is the one that is only got 2 diagonal elements. And that gives us a new fundamental matrix that has just rank 2. When I apply that to the example that I showed you before, you get epipolar lines that look like this. Way, way better. In fact, you can see here the camera was not moving perfectly straight. It was moving off to the side just a little bit in that direction. And here is the epipole. Right? All the epipolar lines go right through the epipole. So we've got the good F, and all is happy in Oz. There are some cool things that you can do when you find the fundamental matrices that relate different views to each other. Okay? Because essentially you can figure out which points correspond to which other points. One, which is really kind of interesting, is suppose I've got a pair of views of a scene, and what I'd like to do is do some stereo. And I know that if I solve for the fundamental matrix, I could, for every point, I could find the epipole that's along and search along that. But, of course, every point lands on a different epipolar line. What you can do is what's called image rectification or stereo rectification, where you take your original image, and if you find the fundamental matrix, you can essentially unwarp maybe that's not the right word. Just rectify is the right word. So it's as if the two images were taken with parallel image planes that are aligned. And why is that good? Because it makes me happy. No, it's good because you can get public. No, it's good because then it means your stereo solution now is just moving along the horizontal line. So your search is not just 1D, because it was 1D before, but it's a particular known one-dimensional search. Namely, every point here corresponds somewhere along the corresponding scan line in the other image. And that was done nicely. Comes from this paper here shown in 1999, showing you a real example that they did that comes from their paper. Here you see two images taken from radically different views of this very weird sculpture. The lines that are drawn on there are the epipolar lines, and you'll notice they're skewed and they go off this way. All right. After you do the stereo rectification by finding the fundamental matrix, you get horizontal epipolar lines, which was the whole point and allows you to do the stereo algorithm. There's some more cool applications. There's a whole bunch of work in building up structures from multiple images taken of that same structure. And there's a system and a whole bunch of work that came out of the folks at Microsoft Research and also University of Washington. Here's an example published at SIGGRAPH. And they built a system called Photosynth. And what you can see here are a bunch of pictures that were taken of Notre Dame. And what these little things down here are meant to show are the locations of the image with respect to the structure. And that has to do with relating between the views that you have things. When you do that, you can do some really cool things. They basically launched this site, this whole phototourism, this idea of that being able to put in your images, and this is their Photosynth. And I encourage you to check it out if when you're using this, we still use computers. In fact, here was a really cool demonstration done by Agarwal and back in 2009. So what you're seeing is there's a whole bunch of these little dots. Those are camera viewpoints of the Colosseum in Rome. You should go see that. I mean, this is nice. See the real one. It's really cool. And this is just flying you around the reconstruction of all these points based upon the solution to where all these cameras were. And this all relates to first solving fundamental matrix issues and then getting the full 3D calibration. I don't want to claim that you could do this with just the fundamental matrix, because in fact you eventually end up getting full 3D reconstruction here. But the idea is you have to know how the points correspond. Summary slide. I love summary slides. For two views, and we learned at the beginning, there's a geometric relationship that defines the relation between rays in one view and rays in the other view. And we were referring to that about the epipolar geometry. These relations can be captured algebraically, besides geometrically. For the calibrated camera case, that was referred to as the essential matrix. For the uncalibrated camera case, it's the fundamental matrix. And the math that we've been going through has been talking about how you can find these matrices, how you can find these relations by just giving me the correspondences between points from one image to the next. All right. This ends the lesson on fundamental matrices. In fact, it ends the entire unit on calibration and stereo. I hope you realize that from these relationships, you can capture the geometry of the scene. That is, given some camera views, you can eventually figure out the three-dimensional locations of the points. So this is not image processing, right? This is actually vision where we recover a 3D structure. And if you're taking the OMS version of this class and you're doing the OMS problem sets, you're going to get to know and love these. Well, you're going to get to know, I hope you'll love these processes pretty well. That's it for this unit. Welcome back to computer vision. With this lesson, we're actually starting a new unit, which I've nominally titled Features in Matching. But really, the whole idea of this is to find reliably detectable and discriminable locations in different images. That is, I'd like to figure out a way that if I have some points in one image of a scene, I'd like to figure out which points are the same points in another image of the scene. Now, you might say, wait a minute, we just did that in stereo. But no, you didn't. You see, in stereo, the idea was that we were going to have these epipolar lines along which we would search. But remember, we talked about that in order to find those epipolar lines, we need to know the fundamental matrix. And in order to do that, we needed correspondences. So this is a way of finding correspondences. That's one way of thinking about it. couple of resources. Forsyth and Ponston cover this nicely here in section 5, 3, and 4. And Salisky, which is that other textbook that we pointed you to, also does this well in chapter 4.